Another application of this concept of expected value. This idea of expected value, or the mean, is how industries such as casinos and insurance companies and so on, that's how they are pretty much guaranteed profit. Like a casino, for example, the games aren't quite fair. So it's always a little bit to the casino's advantage in the long run. Now, you might go to the casino and you might win, but for every person that wins, there are people who lose, and the individuals who lose more than the individuals who win, which is guaranteed by this concept of expected value. That casinos know exactly what the probabilities are and what the bets are, and they're a little bit to their advantage. The same kind of deal with insurance companies. Insurance companies charge rates that are based on the probability that they're going to have to pay. And so the rate they charge is going to be a little higher than what they expect to have to pay based on probability. So in the long run, they're guaranteed their profit as long as they have their probabilities correct, which they do. So this is an example of a life insurance scenario. A life insurance company sells a $250,000 one-year term life insurance policy to a 20-year-old male for $350. So you might be thinking, how can they do that? How can they sell a policy that would pay $250,000 for only $350? In other words, they insure this 20-year-old male, and if the male dies, then the insurance company has to pay his heirs $250,000. Now, if he lives, the insurance company makes the $350. Now, this is a term life insurance policy. Just so there's a little bit of an understanding here, a term life insurance policy is different from a whole life insurance policy. There's different kinds of policies. So like a whole life policy is more like an annuity. You pay into that over a time period, and it's guaranteed to pay out in the end whenever the person dies. A term life insurance policy is a lot cheaper to purchase. But with a term policy, what happens there is the person is buying insurance just for a certain term of time, which is why it's called term life insurance. So for example, if this 20-year-old buys a one-year policy, then that means this 20-year-old is only insured that year. Once this 20-year-old turns 21, the insurance policy has ended. So he would have to buy a new term policy for the next year, and so on. Well, according to the National Vital Statistics Report, the probability that the male survives the year is 0.998734. So that's pretty good news if you're a 20-year-old male. The probability that you're going to live and make it to be 21 is 0.998734. So the probability of the 20-year-old would be 1 minus that. So that would be what? 0.001266, I think. So very unlikely. Compute and interpret the expected value of this policy to the insurance company. So if we're going to compute the expected value, that means compute the mean. So to do this, I'm going to think about the possible outcomes and the probability of that outcome. Now I'm doing this from the insurance company's perspective. So from the insurance company's perspective, there's two possibilities. Either this 20-year-old person lives, or this 20-year-old person dies and they have to make a payment. Now, if the 20-year-old lives to be 21, the insurance company just made a profit of $350 from that particular 20-year-old. And the probability of that happening is 0.998734. Now, the other possibility is that the insurance company has to pay out. So if the 20-year-old dies, then the insurance company has to pay out $250,000. Now, if they pay out $250,000, that's a loss for them. So the loss is going to be the difference between what was paid for the policy and what they have to pay out for the policy. So if I take the $350 that the 20-year-old paid for the policy and subtract off $250,000, what the insurance company pays out for the policy, that would be negative $249,650. So if the 20-year-old male dies, the insurance company loses $249,650. A lot of times people want to say the insurance company loses $250,000. They don't really lose the entire $250,000 because regardless, the person had to pay the $350 for the policy. So again, they would really just be losing the $249,650. And the probability of that happening is 1 minus this, because this and this are complements. So again, if I take 1 minus 0.998734, that is 0.001266. 0.001266 is that probability. So if I'm going to find the expected value, then I'm going to take each outcome times the probability of that outcome. So I'm going to take 350 times this. I'm going to take negative 249,650 times this. Well, 350 times 0.998734, that is 349.5569. So 349.5569. And if I take negative 249,650 times 0.001266, that is negative 316.0569. So negative 316.0569. So if I combine those, that's the expected value. Well, 349.5569 plus negative 316.0569 is 33.5. So adding that up, that's going to be $33.50. That is the mean. Or in other words, that is the expected value. So what does that mean? It says compute and interpret. Well, we've computed. The mean is $33.50. So what does this mean? From the insurance company's perspective, every time they sell one of these insurance policies to a 20-year-old male, they're going to, on average, expect to make $33.50 off of that policy. Now, again, for any one 20-year-old male, what the reality is going to be is that the insurance company either keeps the $350 or they lose the $249,650. So for any one policy, those are the two outcomes. But in the long run, if they insure a bunch of 20-year-olds under this policy, then on average for each one of those policies they sell, they're going to make $33.50. So if they sold 1 million of these policies, then they're going to have to pay out the $250,000 for some of them. But for most of them, they're going to keep the $350. And so again, on average, for each of the 1 million policies they sold, they would make $33.50. So if you're making $33.50 per policy on average for 1 million policies, that means the insurance company is going to make $33.5 million off of those policies. Okay, we're almost done with this section. The last thing we have is that we can also calculate the standard deviation of a discrete random variable. So we can summarize discrete random variable just like we do data. We can find the mean and we can find a standard deviation. So the way we calculate the standard deviation is a lot like the way that we calculated the standard deviation when we had data. We're going to take each outcome minus the mean, and we're going to square that. The difference is what we did when we just had data is we added that all up and we divided by the number of data values, and then we took the square root. Well, instead of adding it up and dividing by the number of data values, we're going to find each of these squared deviations and we're going to multiply it by the probability. And then we're going to add that up and take the square root. So this right here is the conceptual formula. Each outcome minus the mean squared times the probability, and then we add that all up and take the square root. Now this formula here, I'm not really going to talk about, but this is a computational formula like we had also when we were dealing with data. So with the computational formula, if you have to do this by hand, then typically this is an easier computation. So here we take each outcome and square it, multiply by the probability, and add that up. From that sum, we take the mean and square it and subtract. And then that happens to always equal the same value here. And so if we square root that, that gives us the standard deviation. So example, compute the standard deviation of the discrete random variable shots made from the previous examples. Recall that mu sub x equaled 2.39. Well, so I have here just repeated the shots made problem, the 3 free throws, and we're going to again calculate the standard deviation. So what I need to do is I need to take again each outcome minus the mean, square it, times the probability. So in other words, what I'm going to do right here for when the outcome's 0 is I'm going to take 0 minus my 2.39 squared times 0.01. And I'll calculate that in just a minute. Here, I'm going to take 1 minus 2.39 squared times 0.10 because that's the probability. Here, I'm going to take 2 minus 2.39 squared, and I'm going to multiply that by 0.38. Again, the probability. And here, I'm going to take 3 minus 2.39 squared, and I'm going to multiply that by 0.51. So I'm going to write all of those down here. So parenthesis 0 minus 2.39, close parenthesis squared, times 0.01. That is 0.057121. Then I'm going to do 1 minus 2.39 squared times 0.10. And so that is 0.19321. Two minus 2.39 quantity squared times 0.38, 0.057798. And last but not least, 3 minus 2.39 squared times 0.51. And so 0.189771. So if I add that up, that would give me the part underneath the square root. So that's going to be the variance, if you will. So the sum of the x minus mu sub x squared times p of x, and I'll put that in brackets. So 0.057121 plus 0.19321 plus 0.057798 plus 0.189771. So that is 0.4979. So again, what that really is, that's the variance. So the standard deviation is going to be the square root of that. And the square root of 0.4979 is 0.7056202.945. Fortunately, we can use technology to find these calculations. So I've given you instructions here, and I've given you instructions here on how to use the calculator and how to use StatCrunch in order to find the mean and the standard deviation of a random variable. It's somewhat similar to how we did it with data, but it's not the same, and so we got to be very careful. These are very commonly missed because people don't enter this information into the calculator correctly. Now I have here an example using technology, compute the mean and standard deviation for Powerball if the jackpot is $20 million. Since we did this one by hand, I want to go ahead and do this first just to demonstrate and show that we get the same answers, and then we'll do this example. So prior to starting, I entered in list 4 the number of free throw shots made, and I entered in list 5 the corresponding probabilities. So I have this probability distribution entered into list 4 and list 5 on my calculator. So if I want to calculate the mean and the standard deviation for this probability distribution, then I'm going to, again, first of all, I have the data in my calculator, so I got to enter the data in my calculator. I've got the outcomes in list 4, the probabilities in list 5. So now I'm going to go to Stat and Calc, and I'm going to choose one variable statistics like we did when we had data. I get this window. So I tell the calculator the list where I have the outcomes. So I have the outcomes in list 4 for the free throw problem. Now, this is something we haven't done before. For the frequency list, I'm going to tell the calculator where I have the probabilities. So I have the outcomes in list 4, and I have the probabilities in list 5. And I'm going to choose calculate. Now, if you have an older calculator, the command, once you select one variable statistics, then behind that, you're going to put the list where you have the outcomes, a comma, and the list where you have the probabilities. So on an older calculator, the command would be 1 var stats L4 comma L5 if you have the outcomes in list 4 and the probabilities in list 5 like I do. Now, if you look at the results up here, I have X bar. Now that's mu sub X, and that is 2.39. And then here I have the standard deviation, 0.7056202.945, which agrees with what we got by hand. I'll show you StatCrunch for that problem in just a minute as well. Also, prior to starting, I entered into list 1 the outcomes for the Powerball if the jackpot was $20 million. And I have the probabilities that I've entered in list 2. Now, I will point out that it puts some of those probabilities in scientific notation. That's going to happen because they're such small numbers. So with those entered in my calculator, again, the outcomes in list 1 and the probabilities in list 2, if I go to Stat and Calc, one variable statistics, my outcomes are in list 1, the probabilities are in list 2. So if I choose calculate, then I get X bar is 0.38918707763. Let me write that down. That's really mu sub X. So 0.38918707763. And the standard deviation is 1207.10248. So sigma sub X is 1207.10248. So again, that's approximately 39 cents. And the standard deviation is huge, $1,207.10. The fact that that's so big is because there's a lot of variation in what the winnings could be. Now, just for the sake of it, when we calculated this by hand, we got 0.38918,707. Now we got 6.4 here versus 6.3 here. This is a little more accurate, but way out there, it doesn't really matter. And so again, about 39 cents is the expected cash winnings if the jackpot's $20 million. So I just wanted to point out that that agrees with what we got by hand. Now, if I show you StatCrunch, so here in StatCrunch, I have the basketball problem, so the number of free throws made and the probability. So that's the basketball free throw shot distribution. So if I want to do this in StatCrunch, the way I'm going to do that is I'm going to go to Stat, and I'm going to choose Calculators. And the calculator that I'm going to use is a custom calculator right here. So I'm going to select Custom Calculator. Now there's lots of other calculators here that we're going to learn to use later on. We won't learn all of them, but we'll learn a lot of them later on. Right now, we're going to have a custom calculator. So in the window that comes up, where it says values in, I tell the calculator where I have the different outcomes. And the weights in, those are the probabilities. So I have the outcomes in the column I called X, and I have the probabilities in the column I called P of X. And if I say compute, then I get this window. Now, if you look down here, we have a mean of 2.39, and we have a standard deviation of 0.70562029. Both of those agree with both our by hand calculations and the calculator calculation that we obtained. And so part of this tool also is that it creates this graph. And so I can also see the graph that we had found earlier for this problem as well. If I look at the Powerball problem, again, prior to starting, I entered this into StatCrunch. So I have the $20 million prize along with all the other prizes and their probabilities. So I can do the same kind of thing, Stat, Calculators, and Custom Calculator. My values are in the column I've called Cash Prize. Those are the different amounts that could be won. And then the weights are in the column that I've labeled P of Cash Prize. If I say compute, then I get this window, and here's the mean, and here's the standard deviation. Both of those agree with what we got. Well, the mean agrees with what we got both by hand and on the calculator, and the standard deviation agrees with what we got on the calculator as well. We did not calculate that standard deviation by hand.